Right, gents, so with our mathematicians covered the complex arithmetic with us, now what we're going to do today is have a look at some AC network analysis. We're going to look at initially at inductive reactance and how it varies with frequency, do some calculations with a series, a parallel R-L circuit, a resistor inductor circuit. Do the same with capacitive reactance and how that varies with frequency. Most of that is a little bit of revision really from science. Calculation of series and parallel RC circuits. Then we'll look at putting all three components in and analysing an RLC circuit. And through all of that we will prove that all the laws we've already dealt with in terms of Kirchhoff's laws, Ohm's law and everything still apply in an AC circuit. Remembering that when you're analysing you are looking at a snapshot or an instant in time. So although in an AC circuit the voltage is constantly changing apart from when it hits at peak and the current is changing, every moment in time you could apply Kirchhoff's law and it would apply around that circuit. You could apply Kirchhoff's current and voltage laws and they will always apply. And then finishing up, and hopefully we'll get all this done this week, if not we'll finish up next week before we move on, but we'll have a look at how we can use Thevenin's theorem that we've been learning with DC circuits, just if we can apply that to an AC circuit. Okay, so that's the plan anyway. So, reactance and impedance in AC circuits. As soon as we switch to AC, we should talk about what we've been talking about as resistance, or the opposition to current flow. And it's best to think of resistance like that. It's the opposition to current flow. The more resistance we got for a given voltage, the less current we get. We should start to call it really impedance. It's got a symbol Z. It's still measured in ohms, but it becomes a complex quantity in terms of it's now got a magnitude and an angle associated with it. Okay. If we have pure resistance in a circuit, no reactive components that we're coming on to in a minute, so like this, an AC source, an AC current will flow, we'll get a voltage across a resistor. If we draw what's called a phasor diagram of that, where the red, what's the phasor diagram? That phasor diagram. The red line is representing the current flowing in the circuit. The blue line, the applied voltage. Okay, they're drawn, should be over top of each other, but I've just separated them on the diagram on the board so that you can see the length of both of them. So the length of them represents their size, and then the angle between them is 0, because if there's only resistance in the circuit, current and voltage are in phase with each other. The voltage and current peak together. They're like that. And the voltage and current cross the 0 line together in time. Okay, so if we have resistance only, the current and the voltage are in phase with each other. There's no angle between them. If you pass those ones round, they're the slides that I've got up on the board. Oh, did you? Oh, sorry, Mark. I must have. They looked a lot less. None of the diagrams in them, are there? Oh, well. Yeah, it should be. I thought they were. Anyway, so I'm sorry. Never mind. Don't worry. I'll give you some time to take them down. And actually, most of this stuff is in the note pack that I've given you as well. Alright? So, current and voltage in phase. If we look at the power all the time is a multiplication of the instantaneous voltage and the instantaneous current. So we get two positive power pulses with a resistor. Okay, we'll come back to the power shortly. So resistive circuits, you can really just deal with them like you would a DC circuit, because there's no what's called reactive component. Voltage and current are in phase. Ohm's law, Kirchhoff's laws, etc. apply, and you can just deal with it as though it was a DC circuit. Alright? The complication comes when we add some kind of reactive component to the circuit. Inductor. Okay? The instantaneous voltage across an inductor, EL, is given by EL is the inductance in henries, that's L, multiplied by di by dt. What is di by dt? Andrew, got any idea? It's a differential. So it's the, what is the differential? How would we say that in words? Do you remember that it's about the rate of change of something with some other variable? So what that bit is, there, is the rate of change of current with time. Yep. So what happens in this inductor circuit is there's an induced voltage across the inductor that's that's at its peak when the current is changing the most. So when the current has fallen, that's where you get the biggest voltage. So the current slope is 0 at this peak here, so we get no voltage. The current is changing, di by dt is at its highest when we cross the 0 line, therefore we get the biggest voltage at that point, and it's negative. That's where there should actually be a minus sign in front of that, I believe. Okay. Because what happens is the impedance that you get for an inductor is because the voltage generated across it opposes the current that's causing it to happen. Yeah. So as it becomes a reactance, and it's frequency dependent as well, because the faster we make the change, the more voltage we get. Okay. So we're not now a simple quantity, we've got a complex quantity. Because in this circuit, if we say the current here on the phasor diagram is at 0 degrees, the voltage is 90 degrees ahead of it. We talk about going round this angle circle anti-clockwise. Yeah. So if we think about these two vectors going round in a circle, the voltage, EL, is ahead of the current. Can anyone remember from science the word that helps us decide whether current leads or lags voltage? Because if we look at this diagram here, the blue one is E, this is time, voltage peaks before current peaks. Therefore we could either say voltage leads the current, or we could say current lags the voltage. Confusing, I know, but either of those would be correct. And the word that we used in science, I'll do it on a new page, L, CIVIL. This represents inductance, okay, and in an inductive circuit we'd think about covering up the C and I, forgetting about that bit, and in an inductive circuit voltage is ahead of or leads the current, or we could say current is after, lags the voltage. In a capacitive circuit, which we're going to look at in a minute, we forget this L up this end and this I, we forget them bits, and we say in a capacitive circuit, current is ahead of or leads the voltage. We say voltage is lagging the current. Yeah, so that will always apply. We get a situation when we've got both of these things in the circuit, but there will always be one that's bigger than the other and make the overall circuit overall capacitive or overall inductive. Both will have an effect, as you'll see later, but one will always be bigger than the other, and therefore the circuit will either be overall capacitive or overall inductive. And we'll look at that later, and that's another little way to understand whether your circuit and the result you get is correct. If you know which one of those is bigger, which got the bigger reactance, am I getting a result that complies with civil? Okay, so that word is really handy. So in this inductive circuit, if that's a pure inductor, and you can't get one in real life because an inductor is a coil of wire, the coil of wire's got some resistance as well, okay? But if you could get a pure inductor, there would be a completely 90-degree angle, phase angle, between current and voltage. A positive 90-degree angle. That's that there. Okay? Everyone happy with that? So if that voltage was 6 volts, we'd say 6 volts at angle 90 degrees. That's how we would write it. Yeah. The current might be 2 amps angle 0 degrees, and that's how you write it. You put the size of the quantity with its units, followed by the angle sign, followed by the angle in degrees or radians. Yeah, if the degrees symbol is missing, the implication there is that that's radians. Okay. So that's what's happening. So for an ideal inductor, the current lags the voltage by 90 degrees. Equally, we could say the voltage leads the current by 90 degrees. If we look at the power in such a circuit, what we get is we get a positive half cycle here and a negative one there, then a positive and then a negative. And the actual overall power dissipated in a pure inductor is a straight line 0, because all of those, in that part we're dissipating some power, in that part we're giving it back, then we're dissipating, then we're giving it back. Everything, an inductor uses no useful power at all. It does not convert energy into heat or anything like that. You can only get power from a resistance. Okay? Everyone happy with that, yeah? There's our civil. We might come back to that in a minute. Inductive reactance. So we've got this effect. The inductor causes the out of phase relationship. And the inductor has an impedance Z, where its magnitude is the inductive reactance XL. So the size of the impedance is XL ohms. So if we're going to talk about that, we would add the J to make it the impedance. Then it's got its angle. Okay. So XL is the positive real part of an impedance. And you can calculate XL in one of two ways. 2 pi times the frequency times the inductance, or omega times the inductance. Omega, whenever you see that in an electrical circuit, it is always equal to 2 pi f, and its units are radians per second. It's called the angular frequency of the circuit. And quite often, it's in fact, the biggest majority of the time, it's easier to work in omega initially and only use that formula if you want to know what the frequency f is in hertz. Because it just takes pi out of the equation. Yeah. Makes the numbers less difficult. So if you can, if you're given that in omega, if you see a value something times pi, it means it's in omega. What you do have to be careful of there is you're then going to have your calculator in radians mode when you use your angles. Alright? So, if we look at because of this frequency in here, that value XL is frequency dependent. It goes up and down with frequency. An inductor, XL rises as frequency rises. So, what this means for your electrical circuit is, at 60 Hertz, a 10 millihenry inductors would measure 3.77 ohms impedance. At 120 Hertz, 7.54 ohms impedance. 2500 is 157 ohms. So as you increase the frequency, the resistance or the opposition to current flow in that inductor goes up. What's going to happen to the current? Down. Yep. So as you increase frequency in an inductor circuit, the current's going to fall. And although there's a lot of maths in this, try and get an understanding of the underlying electrical principles of what happens when we change things in AC circuits. So that's what's happening. As we increase frequency with an inductor, we actually increase its impedance in the circuit, and therefore the current falls. Oh my god. So, if we look at a typical circuit, it's got 10 volts at 60 Hertz, an inductor of 10 millihenries. You can find out that XL is equal to 2 pi FL, with the calculations, 3.77 ohms. Therefore, the current flowing is given by, and this is just the magnitude of the current, we've not used any complex numbers here, E10 divided by 3.77, 2.65 amps. If I wanted to add the angles to these, what would I add? I've quoted 10 volts, 60 Hertz. What do you think the angle is we use there? If you're not given one, the only thing you can do is assume it's 0 degrees. Yep. What's the angle for XL? Can you remember from the previous slide? Yeah, the angle 90 degrees. I need to orient this board. Yep. So now doing the complex arithmetic, 10 divided by 3.77 still 2.65 amps. Angle, and then how do we do this? Naught. How do we do? What do we do with the angles when we divide into two polar complex numbers? We take the bottom one away from the top, so it's the minus 90 degrees. So the current in this circuit is lagging the voltage by 90 degrees. Does that fit with civil? Inductive circuit, current is after, lags the voltage. Okay? That's where I said that's a useful check to be able to do that, is make sure that your circuit fits and is complying with this when you're finished. Because if you make a mistake with one of your angles, you could be out. If we use the complex arithmetic, we do 10 angle 0 degrees divided by 3.77 angle 90 degrees, because the inductor XL has got an angle of 90 degrees associated with it. Yeah, always. And we still get the 2.65 amps, but then we say it's got an angle of minus 90 degrees, and that fits in with our word civil, because in the inductive circuit the current should be lagging the voltage. Yeah. So there it is on the next slide. Okay. And if you convert that, so if in your calculators, just convert 3.77 angle 90 in polar form to rectangular form, and you get 0, should get 0 plus 3.77J, because the inductance is all imaginary number, all unreal part. Okay. Yeah. So, if we then introduce a circuit where it's got, and this is where we'd always have this with a real inductor anyway, because it's got some resistance. So if we model a real inductor by saying this is a 10 millihenry inductor where the coil resistance is 5 ohms, for instance, they're in series with each other. We then get a more complex phasor diagram. In a series circuit, there is only one current because they're in series. So generally, you would make the current what's called the reference phasor, or the one with 0 angle in a series circuit. And then you would say what are the angle of the voltages from that 0 current. So you'd say the voltage is leading or lagging the current in that circuit. So we got our current phasor in red there, and then the 3 voltages. So we got the voltage associated with the resistor. Magic pen, turn the magic pen off. Told you, Mark, didn't I? There you are. We talked about that being in phase with the current. So that's this one here. We've got the voltage across the inductor, EL, 90 degrees upwards, leading the current by 90 degrees, which it does in an inductive circuit. Yeah, think civil. And then what we get from that, if we make that into a parallelogram and draw the vector to that point, we end up with ET, the applied voltage in this case, or the resultant voltage for that vector. Yeah. So we got a voltage applied that's out of phase with the resistive voltage by 37 degrees. We'll find out in a minute. Okay. Because what we can do, and I've done this a little bit in the notes, is create a table and then fill in what we know and calculate all the other results. So we know we're applying, for instance, 10 volts, and 10 volts plus 0J ohms, okay, 10 angle 0 degrees. The impedance of the resistor, Z, is just 5 ohms, 5 plus J, 5 angle 0. So I'll put them in both forms in the table, just in case we need them. The capacitive, why have I got C in there when I'm talking about an inductor? It has gone wrong, severely wrong. I'll cut that bit out of the video. So this is actually the impedance of the inductor is 3.77 naught plus 0.77 J or 3.77 angle 90 degrees. That's how we would express that. Okay. Now, to calculate the total impedance of this circuit, what impedances have we got in that circuit? How do we normally calculate total impedance? We've got an R and we've got XL associated with this. If they were two resistors, how would you calculate the total resistance? You'd add them together. No different with this. The total impedance of this is the resistance 5 plus 0J added to 0 plus 3.77 J. Yeah, it is in fact R plus XL J ohms. Yeah. So that equals 5 plus 3.77 J ohms. These numbers must have units as well, gents, by the way. Now we're in talking about, earlier when Mark was working, you just talk about numbers. Now we're talking about electrical quantities. They must have units. So in the rectangular form, the units go on the end. In the polar form, the units go in there. Yeah. Okay. What have I got on here? Oh. So that's what the total impedance is in that circuit. Okay, so we can put that in here. 5 plus 3.77 J ohms. Do convert that to polar as well, gents, please. .3 ohms, angle 37 degrees. Yeah. Okay. So now we've done that, we've got a voltage, and we've got a current, we've got a resistance. We can find the current, can't we? It's going to be that voltage to the Ohm's law. E divided by I. We need to use them in complex form. So we've got them both in polar form, so we might as well do 10 angle 0 degrees divided by 6.3 angle 37. So let's have the result of that, please, gents. 10 over 6.3 is amps, angle minus 37 degrees. Yep. So the current lags the voltage by 37 degrees. Is that right? Yeah. Does that work with civil? Yeah. Does it work with the phasor diagram I had earlier? There's the voltage. Okay. What we're saying is if we shifted the voltage, so the voltage was at 0, the current would be down here, 37 degrees behind it. Or we could say the voltage leads the current by 37 degrees, makes no difference. Okay? You only need angles when you're talking about two different quantities and want to know what the phase relationship between them is. If you're only interested in how many amps it is, you're not bothered about the angle. If you want to know what the relationship between two vectors is, then you need the angles. Okay? So that's what we got in that circuit. The blue is the voltage E. The dashed red line is the current. And the current is lagging the voltage by 37 degrees. Okay. Moving on swiftly, we could do exactly the same thing with parallel circuit. Okay. So what I'd like you to do is see if you can calculate. We've got a 10 volts applied. There's our voltage. We've made that the reference phasor this time because it's common to both components. We've got a 5 ohm resistor in parallel with a 10 millihenry inductor. Alright. Can you do the calculations to find the overall impedance of that circuit Z and the current flowing in that circuit? So have a go at that, see if you can make a start on that and find those values. You're going to do parallel resistance formula or parallel impedance formula, okay, and calculate the total impedance and the current in that circuit. What we got is XL 2 pi FL, isn't it? Yeah. So that's 2 pi times 60 times 0.01 millihenries. Yep, that comes out at 3.77 ohms. Yep. Yeah. Yes. Yeah. So we're talking about ZT is equal to what's the easiest thing to use here, do you reckon? Product of a sum. So we're talking about, remembering we've got to use complex quantities. So R is 5. There is no J part. L is 0 minus, sorry, plus 3.77J. And then that is over 5 plus 0 plus 3.77J. So there's multiply on the top. So you've got multiplication of those numbers, addition of those numbers, and then eventually divide those numbers to come up with the result of that. So you've been doing that earlier, so I'll give you 5 minutes to come up with the result of that in rectangular form, and convert it to polar as well. So from this point, having multiplied the top and added the bottom, we've now got to multiply this out to get rid of the J term underneath. So we've got to do 18.85J multiplied by 5 minus 3.77J. We've got to do that on the top. And on the bottom, 5 plus 3.77J times 5 minus 3.77J. Yeah. And what happened here? Remember, this is always, the result of this is always the J disappear, and the result is these two, this number squared plus that number squared, a constant. Yeah. Because 3.77 times minus 3.77 is a negative number, but then that's multiplied by J squared, which is minus 1. So you end up with two positive numbers added together there. Right? So the result of that bottom is 5 squared plus 3.77 squared. And the result of the top is a bit more messy than that. What we got then, gents, for this top line? Those two multiplied together. Plus what? Jack, say that again. Yeah. Well, I'm saying yes. I don't know. Would everyone else agree with that? Yeah. So then, what is that in terms of what is 71.06 J squared? $94.25 J, yeah? Plus 71.06 J squared. So that must be minus 71.06, yeah? Plus 94.25J on the top. And what is 5 squared plus 3.77 squared multiplied out? $39.2. So then the final result of that is you split it. So you do minus 71.06 divided by 39.2. And 94.25 J divided by 39.2. So here we divide the 71.06 by 39.2 and get the real part of the result. Divide 94.25 J by 39.2, get the imaginary part. What is that if we convert that into polar form? Three. Angle 127 degrees. Does that look right? Negative real part, positive imaginary part. What quadrant's that in? Yeah. Okay. Yes, and okay. So from that we've got an impedance 3 ohms angle 27, or if we want it in that form, minus 1.81 plus 2.4 J. Okay. So now we're looking for our current. E divided by I. So do that in complex form and find out what the current is in this circuit. So for the benefit of the video, we've gone wrong up here. That was a positive sign in here. This is negative 71. Meaning when it comes down here as positive, we end up with a plus 1.81 plus 2.40 J. That angle is 53 degrees. Where I noticed that was going back to the original phasor diagram and knowing the circuit is inductive and therefore the impedance should have a positive angle between 0 and 90 degrees. Can't go beyond the 90 degrees of a per inductor. So the 127 degree angle, immediate flag come up there saying something's wrong here. Just see how much just missing, getting one positive or negative sign wrong can mean you get the answer totally wrong. So where are we going here then with this voltage? What is the voltage in polar form for this circuit? $10 volts, no angle, so it's 10 angle 0 degrees, and that's not, I can't even get the ohms law right today. E over Z, Z is 3 ohms angle 53. Ten divided by 3 is 3 1/3. Amps angle must be minus 53 degrees. Does that fit with civil? Current lags voltage in an inductive circuit? Yep.